Ever wondered how one of the earliest, most ambitious online worlds, Ultima Online, actually worked behind the scenes? I mean, how did thousands of players connect and interact in a single, persistent world back in the late 90s? The internet was still pretty much dial up for most folks then.
It's a fantastic question, and honestly, delving into it takes us right to the foundations of online gaming. A lot of the core challenges and, frankly, the ingenious solutions they came up with back then, they're still shaping how modern online games and even bigger distributed systems are built today.
That's a really key point, and it sets up perfectly what we're trying to do in this deep dive. We're going to pull back the curtain on Ultima Online's network communication, really try to demystify that complex dance between the game clients and the servers.
Yeah, the goal is to get a solid foundational understanding of those pioneering technical bits, see where they came from, how they tackled problems no one had really solved at that scale before.
Exactly. And then we want to pivot and see how those very same principles, awfully painstakingly reverse engineered and documented by dedicated fans, are being used, recreated, even improved upon in modern software projects. We're talking specifically about the vibrant communities building emulators like ServUO, ClassicUO, and Orion.
Right, it's almost like digital archaeology, isn't it? You're digging into the past, uncovering these surprising facts, these insights that, still hold up today.
Totally. And to help guide you, the listener, through this, we've pulled together a really diverse set of sources. We've got everything from a super technical thesis out of Spain on actually reverse engineering game protocols.
Which is fascinating stuff, by the
Yeah,
way.
absolutely. And we also have direct insights, historical accounts from UO's original designers, people like Ralph Koster, Tim Cotton. You get their perspective.
And importantly, we're also looking at current discussions. What people are saying right now in community forums, places like Reddit, Hacker News, where folks are actively building and refining these modern emulators.
So hopefully that mix gives you a really holistic, kind of layered view of UO and its incredible lasting legacy.
Okay, so where do we start? Maybe with the big challenge that UO and really all online games face, preservation.
Yes, let's unpack that first. Preserving online games is, well, it's often called a real thorn in the side for game preservationists, isn't it?
It really is.
Yeah.
The inherent difficulty, it comes down to their dependence on third-party services,
Yeah.
specifically those original game servers.
Right. The servers run by the publishers or developers.
Exactly. And those servers can just disappear. They get shut down.
Mm.
And if the game wasn't designed from the start with some way to play offline or allow community hosting, which most weren't back then,
Then the game just dies. It becomes unplayable. A digital ghost.
pretty much lost to history. And the core technical reason for this often boils down to those proprietary application layer protocols we mentioned.
Like a secret handshake, a custom language only the client and server understand.
Precisely. And it's a language that's constantly changing with updates and patches. Plus, and this is the killer, publishers almost never release the server-side software, the actual code that ran the world.
For business reasons, sure, but it means when the game ends its official life, that critical logic, all the server assets, poof, gone.
And that leads directly into why game server emulation even exists. It's a direct response to that preservation problem.
The goal being to basically build a replacement server.
Essentially, yeah.
Yeah.
You analyze the original game, figure out its secret language, its protocol, and then you implement a brand new server that mimics or emulates how the original one behaved, so the old client can talk to it.
Okay, so the two main goals for these projects are, first, reverse engineer and document that whole network protocol.
Which is a massive undertaking in itself.
Right. And second, develop a compatible game server, ideally without having to change the original game client at all. Get the old software talking to the new backend.
And the payoff, beyond just preserving the game, is the incredible knowledge you gain. You get this deep, practical understanding of how game servers, network protocols, how these complex distributed systems actually work. It's hands-on digital archaeology.
Which brings us right back to Ultima Online itself.
Yeah.
You simply can't talk about pioneering online games without talking about UO. When it launched in '97, wow, it was revolutionary.
Absolutely. As an MMORPG, it gave players this truly open, persistent world where your character could, live and exist in a way no game had before. Building houses, running shops, the social
It
dynamics,
wasn't just about quests, you were shaping the world.
and the scale required for that in 1997. Astounding. Thousands of players at once. A massive, seamless map. What was it? Over 29 million square meters.
Something like that, yeah. It was huge.
That sheer technical challenge forced innovations, things in network architecture, game design. Stuff that didn't just influence later games, but even broader computing concepts we still use. Understanding UO's network isn't just history, it's seeing the birth of solutions to problems we still face in distributed systems today.
So how did they manage it back then? It all starts with that fundamental relationship, that dance between the game client and the game server.
That's the bedrock. Your game client, that's the software on your PC. It's your window into the game world. Its main jobs are, first, taking all your input keyboard, mouse clicks, telling your character to move, attack, cast a spell.
And then it has to understand the data coming back from the server,
Yeah.
right? Decode it, figure out what's happening around you.
Exactly. It analyzes that game world data, displays the information back to you from your character's perspective, so you see your health, your inventory, the players and monsters nearby.
And it's constantly updating based on what the server sends. Like if someone else moves, the server tells your client and you see them move.
Right. It might pull static stuff like your stats or the look of map objects. And it sends your actions, I want to attack this, to the server.
Okay, so the client is the window. What about the server?
The server is the authority. It's the absolute source of truth for everything happening in the game world. It maintains the single, consistent state.
So while my client shows my view, the server knows the real state of everything.
Precisely. It receives all those inputs from all the connected clients, processes them according to the game's rules, calculates the new world state, who moved where, who took damage, what loot dropped, and then it sends the relevant updates back out to each client so their view stays accurate and synchronized. It's a central coordinator.
Which leads us to that critical security principle in multiplayer games. Don't trust the player, or rather don't trust the client.
Exactly. Sounds harsh, but it's fundamental. In a single-player game, if you cheat, give yourself infinite gold, whatever, you only affect yourself. But in a multiplayer game,
A cheater ruins it for everyone else. Messes up the economy, PvP, fair play.
so the server must be authoritative. Let's say you use a hacked client that tells the server, hey, I have 10,000% health. The server knows your real health based on its own data when you take damage.
The server calculates it based on the real value, and you die when you should, regardless of what your hacked client is showing you.
Exactly. Or think about movement. Your client can't just send a message saying, I'm teleporting across the map through this wall. No, it sends an intention. I want to move forward.
And the server checks that intention. Is there a wall there? Can they move that fast?
Right. The server applies the rules, determines the valid outcome. Maybe you move one step, maybe hit the wall, and then it sends the updated correct position back to your client. That authoritative model is absolutely key to preventing tons of common cheats. It's about game integrity.
Okay, so this client-server chat happens over the network. How does that work technically? You mentioned layers.
Yeah, we often talk about network layers using the OSI model Open System Interconnect. It's just a way to conceptually break down network functions. Game programming usually happens way up at the application layer, dealing with game logic.
But decisions lower down matter too, right? Like TCP versus UDP.
Hugely important. That's the transport layer. Choosing between TCP's reliability and UDP speed is a massive trade-off in game development.
And UO, like a lot of games then, and even some now, like Tanky Online, apparently, didn't just use standard web protocols. They built their own language on top.
Exactly. A proprietary application layer protocol. Custom rules for how game data was packaged, sent, interpreted, built on top of TCP, usually. And it's that custom, often undocumented nature that makes reverse engineering such a specific challenge for preservationists and emulator devs.
So digging deeper into UO's architecture, we hit something really groundbreaking they did for scale. Sharding.
Ah, yes, sharding. And here's a fun fact. You hear sharding all the time now with databases, right? Horizontal partitioning.
Yes, splitting data across servers.
Well, the term sharding, as applied to server architecture for online worlds, is widely credited as being coined by the Ultima online designers. The technique existed before. Sure, partitioning data goes way back. But the name, that came from UO.
No way! Why did they call it that?
It was tied into the game's lore. There was this world crystal that shattered into pieces, into shards. And those shards represented the multiple parallel copies of the game world, the different servers or realms players were on.
That's brilliant, taking a technical concept and giving it this cool, in-world name.
It stuck. And it wasn't just a name, it was how they solved the massive load balancing problem. How do you handle thousands of players on one huge map without constant loading screens or jarring zone transitions?
They came up with these area serves, right? Seamless submaps.
Exactly. Rectangular, seamless submaps, each run by its own server process, an area serve. So you could just walk across the world, and you'd seamlessly transition from one area serve control to the next. mostly seamless anyway.
How did that work behind the scenes? It sounds tricky.
It was. They used what they call mirror code. When you, or even a monster, crossed an area served boundary, the system had to carefully copy your character's entire state, all your stats, inventory, position.
Send all that data in a bundle to the new area serve taking over.
Right. And only once that transfer was confirmed, it would destroy the old copy of you on the area serve you just left. That handoff had to be perfect to avoid losing data or duplicating characters.
And coordinating all these area serves was the job of the game serve.
Yep, the game serve was the central hub. It handled logins, directed players to the right area serve based on where they last logged out, and managed the overall shard state. It was pretty sophisticated distributed engineering for 97.
Though I remember hearing some of those boundaries could be super laggy, especially in crowded spots, like parts of Buccaneer's Den.
Oh, absolutely. The way the world was carved up wasn't always perfect from a load perspective, and those themes could definitely become bottlenecks, leading to lag and, as we'll see, some interesting exploits.
Now, one of the most mind-blowing things about UO's original setup, they didn't use a normal database.
Isn't that wild? No traditional relational database for the main live game state, which is completely different from how almost any modern online game works. They rely heavily on databases.
So how did they save player progress? Where did the world state live?
Okay, get this. Each shard, each game world instance, had a daily shutdown and backup. During that maintenance, the entire live game state of every single area serve was just dumped straight from memory into one enormous binary backup file.
Like a giant snapshot of everything.
Exactly. By the mid-2000s, these files were apparently around 4 gigabytes each, just a huge binary blob. The game server would then tell the area servers to load their last good backup file when they restarted.
Wow. So the data only really made sense inside the running game. You couldn't just query it easily from the outside?
Precisely the problem. You couldn't run standard SQL queries on those binary blobs to find out, say, who owned which items, or how many of a certain rare sort existed. This no-database approach created huge challenges, especially when they needed to track down exploits, like item duping. It forced some very creative solutions.
Okay, so data's moving between client and server. It's being saved in these massive blobs. How did that network communication actually happen? It's all about packets, right?
Fundamentally, yes. Online games, like everything on the internet, use packet switch networks. Data gets broken into small chunks called packets. Each gets addressed, sent out, and hopefully reassembled correctly at the other end, like setting a book one page at a time.
And designing the protocol, the rules for those packets, involves a lot of decisions.
Oh, yeah. You got to figure out packet size and format how the data is laid out. You need handshaking that initial hello to set up the connection, acknowledgments confirming packets arrived, error checking, maybe correction, compression to save bandwidth, which was precious back then, and encryption for sensitive stuff.
So what did a typical UO packet look like?
Usually they'd start with a header. Key info right at the front, like a packet ID, a unique number identifying the type of message, and often the packet's total length. That header lets the client or server quickly figure out what kind of data it's just received and how to process it.
Can you give some examples from UO, like specific packet IDs?
Sure, looking at lists documented by the community, like from Penultima online sources, you'd see things like 0x02, which was a move request. That's the client telling the server, I want to move this direction.
Okay.
Then maybe 0x03 for a talk request, the client sending a chat message. Going the other way, the server might send 0x20, draw game player, telling your client to display another player character on screen.
Makes sense.
Or 0x1c, send speech, which is the server sending a chat message to your client. There were also utility packets, like 0x73 for a ping message to check latency, or 0x80 for the initial login request, each ID mapped to a specific function.
And when you're dealing with these raw binary packets, there's that tricky thing called endianness, right?
Ah, yes. Endianness. That's a classic headache in low-level networking and file parsing. It's about byte order. Does a system store the most significant byte of a multi-byte number first, big endian, or the least significant byte first, little endian?
Like how a number like 1,000 is stored in memory.
Exactly. A 16-bit integer representing 1,000 might be stored as, say, bytes 03 E8 in big endian, but E803 in little endian. If the client, maybe little endian by 86 PC, reads a packet sent by a server that used big endian, and it doesn't correctly swap the bytes.
It gets complete garbage data. That number 1,000 could be misinterpreted as something totally different.
Precisely. You have to know the endianness of the data source and convert it if necessary. It's crucial for correctly reading item IDs, coordinates, stats, everything. A single byte swap error can break everything.
Okay, beyond just the structure, what about security? Was the communication encrypted?
Yes, after an initial handshake phase where things were sent in clear text, encryption would typically kick in. We can look at the Tanki Online example from one of the sources as a modern analogy for how this might have worked, principle-wise.
So how did that tanky handshake go?
Well, the client would first send some basic info language, OS, in a clear request. The server responds with SVHash response. Critically, this contained a 32-bit hash value and an encryption flag. It also sent an svOpen space message with a unique 64-bit space ID.
Okay, hash and space ID from the server.
Then the client confirms with CL space opened, and boom, from that point on, the communication switches to encrypted.
And the encryption itself, what kind was it in that tanky example?
It was an XR-based stream cipher. It took that 32-byte hash and the 64-bit space ID, combined them somehow to create an initial seed. This seed was then used to initialize two arrays of bytes, essentially pseudo-random key streams, one for server-to-client data, server sequence, one for client-to-server, client sequence.
So it wasn't just a simple XR with a fixed key.
No, it's more dynamic. As data was encrypted or decrypted, bytes were pulled from these sequence arrays using some kind of selector logic, and those bytes were XR'd with the actual data byte by byte. The key stream changed constantly based on position and these sequences.
But wait, you said the hash and the space ID, the things used to create the seed for these key streams, were sent in clear text during the handshake.
Exactly. And that's the major weakness. That's security through obscurity. Because the fundamental secrets needed to reconstruct the entire key stream, the hash and the space ID were transmitted openly at the start.
Anyone listening in could grab them, calculate the same initial seed, generate the same server sequence and client sequence, and decrypt everything afterwards.
Pretty much. It made it vulnerable to a classic man-in-the-middle attack. You could intercept, decrypt, maybe even modify and re-encrypt traffic. It suggests the encryption was likely more intended to stop casual snooping or make simple packet sniffing harder, rather than providing robust, serious data protection. Which is a bit worrying if things like passwords were sent over that channel.
Yeah, that doesn't sound ideal. So given all this complexity, the custom protocol, the weird database situation, the potentially weak encryption, how on earth do emulator communities like ServUO even begin to figure all this out? How do you reverse engineer this realm?
It's a fascinating mix of techniques, really. A blend of art and science. One of the absolute cornerstones is packet sniffing.
Using tools like Wireshark to just capture the traffic?
Exactly. You capture everything going back and forth between a working original client and an official server, if one still exists, or using old logs. These captures, these packet dumps, become invaluable historical records. You can analyze them later, even if the servers are long gone.
How do you make sense of the raw data, though?
That's where careful observation comes in. You perform a specific action in the game, move one step north, say hello, drop an item while capturing packets.
Yeah.
Then you look at the captured data around that time and try to find the packet that corresponds to your action. Slowly, you start identifying packet IDs and data structures.
What if encryption gets in the way?
That's where code patching can come in. This is more advanced. You have to dive into the game client's actual compiled code, find the functions responsible for encrypting outgoing data and decrypting incoming data.
And modify them. Patch the game.
Right. You patch the code to, say, dump the plain text data to a file or debug console before it gets encrypted or after it gets decrypted. This was sometimes done using special debug versions of runtimes, like the Flash Player Debug Projector, to get the necessary access. It lets you bypass the encryption layer entirely.
Okay, sniffing and patching. What else?
There's static analysis. That means examining the game's executable files, the binaries, without actually running the game. Using tools like disassemblers or decompilers, you try to understand the code's logic, maybe find the encryption algorithms, figure out how packets are built or parsed.
What are the limits there?
Well, it's hard to understand server-side logic just from the client code, and if the game dynamically loads code or data from the server, static analysis might miss that if the server isn't available. It gives you clues, but rarely the whole picture.
So you might need to see it running.
Which leads to dynamic analysis. Using a debugger to step through the code while the game is running. You can inspect memory, see exactly how data flows, watch the encryption routines in action.
But don't games try to stop debuggers? Anti-cheat stuff.
Oh, absolutely. It often turns into a real cat-and-mouse game. The game tries to detect the debugger, the reverse engineer tries to hide the debugger or bypass the detection. It's a constant battle.
Across all these methods, is there a core principle?
A key principle is the known plaintext attack, especially combined with packet sniffing. If you know exactly what action you performed, the plaintext input or expected output, like setting the chat message test 1234, you could look for corresponding patterns in the captured network data, the ciphertext, even if just obfuscated binary.
So you send test 1234, capture packets, look for something that looks like that message encoded, and figure out which packet ID means chat message and where the text data is stored within it.
Exactly. You do this repeatedly with different actions moving, using skills, trading items, and slowly, painstakingly, you decode the protocol piece by piece.
And once you understand that protocol, that secret language,
It unlocks everything. You can then start reverse engineering the actual game mechanics based on the messages exchanged. How does casting a spell work at the network level? How does the server tell the client about item properties? How do they keep the game state synchronized between everyone? That deep understanding is what makes accurate emulation possible.
and sometimes this level of understanding led to some pretty wild stories back in the day, right? Like dealing with exploits.
Oh, definitely. There's a fantastic, almost legendary anecdote from UO's history that perfectly illustrates this, how deep protocol understanding and server-side ingenuity were used to combat a massive problem. Item duplication, or duping.
Ah, the classic MMO nightmare. How did duping work in early UO?
It was often tied to those area served boundaries we talked about, especially laggy ones. A common method involved dropping a valuable item right near a boundary, then trying to pick it up exactly as you crossed over, triggering that mirror code handoff while the server was lagging.
And if the timing was just right.
If the timing was just right, the lag in the synchronization logic could glitch. The original item might fail to get deleted properly on the first area serve, while a new copy got created on the second one. Voila, two items where there should only be one. This flooded the economy with illicit copies of rare items, totally undermining legitimate players.
And the developers couldn't just search a database for these duped items
Because
because
there was no easily queryable database. Remember, the entire world state was in those massive, opaque, binary blobs saved daily. They couldn't just run a SQL query like select from items where name dupe sort and count one. The tools didn't exist for that kind of ad hoc analysis on the live or backed up state.
So how did they possibly track them down?
They came up with this incredibly clever invisible ink system. It leveraged the daily server load process. Before the area serves fully load the world state from the binary blobs, a special preload script would run.
What did this script do?
For valuable or unique items, it would check if the item already had a special tag, an objvar, object variable, basically a custom piece of data attached to that specific item instance. If it didn't have this tag,
Script would add one.
yes, it would generate a unique hash value derived from things like the current time, the ID of the area serve the item was on, and the main game serve ID. This unique hash was then stored on the item itself as this new objvar. Think of it like a unique serial number generated at load time.
Okay, so every valuable item gets a unique fingerprint when the server starts up. Then what?
That unique hash was also sent immediately to the main game serve, which kept a temporary lookup list in its memory just during the server loading process. Now here's the crucial part. If, during that same loading sequence, the game serve received the exact same hash for a second time.
It meant it had found a duplicate. An item with the identical origin fingerprint had appeared again in the world state blob.
Bingo. That was proof positive of duplication. When that happened, the system would permanently mark the duplicated item, and often the original too, just to be safe, with another objvar, this one containing the simple text string. I am DGP.
And that flag was visible too.
To the customer service GMs, game masters. They could now easily identify duped items just by inspecting them in-game. The temporary hash lookup table was cleared after the load finished, so it was memory efficient.
That's ingenious. So they tracked them for a while, then what? The dramatic part?
Oh yeah. After weeks of silently tagging items and identifying the players holding large quantities of them, they executed a mass banning of known dupers. Thousands of accounts sometimes. But they didn't stop there.
What else did they do?
They ran a custom script on the properties, the in-game houses, owned by these banned dupers. This script didn't just delete the house, it recursively deleted everything inside it. Then it replaced the pristine plot of land with graphical sooty rubble. And it didn't stop there either. It often generated special eternal fire fields on the plot graphical fire effects that players couldn't put out. And the final touch. It placed a straw training dummy on the rubble, prominently labeled an effigy of a traitor.
Wow. That's incredibly public shaming.
Totally. And they did this in batches, server by server, so players would log in and see the smoldering ruins and effigies where known dupers' houses used to
Mm.
be. It was a powerful, visible deterrent, a direct consequence delivered within the game world itself. A legendary moment in MMO history, really.
It's fascinating how that solution, marking unique items with hashes to detect duplicates, kind of echoes modern concepts, isn't it?
It really does. You think about marking non-fungible items with unique, time-stamped identifiers. It has parallels to the ideas behind
Yeah.
NFTs or using blockchain-like ledgers for ensuring authenticity and preventing duplication.
Like using a secure ledger, maybe something like Amazon QLDB, or even concepts from Bitcoin's proof of work, to validate when currency or items are created.
Exactly. Now, applying full blockchain tech to MMOs has its own massive performance issues and complexities, so it's not a magic bullet. But the core problem UO faced, guaranteeing uniqueness, preventing illicit copies, timestamping events, is the same kind of problem driving innovation in distributed ledger technology today. It shows how fundamental these challenges are.
So all this deep understanding gained through reverse engineering and dealing with these historical challenges directly feeds into the modern emulator scene, building a new Britannia, so to speak.
Absolutely. These community projects, Classic UO, Orion, Serve UO, they're the direct inheritors of all that painstaking analysis and knowledge built up over decades. They're actively preserving and evolving the game.
And it's important to note, they're not usually working from stolen original source code, right?
Generally, no. That would be legally problematic and often technically impossible anyway. Their approach is based on studying those network packets we discussed, meticulous observation of how the original game behaved, and often how it misbehaved. Replicating original bugs is key for authenticity,
Yeah.
and leveraging that huge repository of community knowledge and memory.
It's collaborative digital archaeology, really.
Precisely. And they're building these emulators using completely modern tools and technologies.
Like .NET and .NET Core for projects like Classic UO and Modern UO clients, and Serve UO on the server side.
Exactly. Using modern managed languages and frameworks. It's a far cry from the C++ and assembly of the original era. We saw the analogy in the sources with the Tanky Online server emulator built in Java, using the Netty framework.
What does something like Netty give you?
Netty provides a high-level, event-driven abstraction over the raw network sockets. It handles a lot of the tricky asynchronous I/O, threading, buffer management, letting the developers focus more on the game logic and implementing the specific UO protocol, rather than wrestling with low-level network plumbing.
And these modern projects use clever software patterns, too. You mentioned a type adapter pattern.
Yeah, that was highlighted in the Tanky project description. It's an elegant solution for handling the encoding and decoding of these custom binary protocols. Instead of scattering parsing logic everywhere, you create specific adapters for each data type or object.
Like a player adapter that knows exactly how to read player's data from a raw network buffer, from buffer, and how to write a player object back into the correct binary format to buffer.
Exactly. It encapsulates all that complex byte manipulation, Indianness conversion, handling optional fields, non-null optional wrappers were mentioned. It makes the main networking code much cleaner, more maintainable, and less error-prone when dealing with complex binary structures.
And this helps enable things like RPCs, remote procedure calls.
Yes. With good serialization handled by adapters, you can create systems where the server code can almost directly call functions on the client, and vice versa, despite them being different programs potentially written in different languages, like Java Server and ActionScript Client, or .NET Server and original C++ client.
So the server might have code that looks like client interface, display message player, hello, and the system handles packaging that call and the parameters into the right packets, sending them and triggering the corresponding code on the client side.
That's the idea. It creates a much more seamless bridge between client and server logic, hiding some of the raw network communication complexity.
Of course, building an accurate emulator isn't just about mimicking the protocol. You also have to deal with the fundamental realities of networks, like lag.
Latency, the great enemy of online games. You can't eliminate it, but you can mitigate its effects. Modern games and emulators use techniques like dead reckoning or client-side prediction.
Where the client basically guesses where other players are moving?
Sort of. It extrapolates their movement based on their last known velocity. So, on your screen, other players keep moving smoothly, even if you haven't received a new packet from the server about them for a fraction of a second. if the server update eventually shows they went somewhere else.
The client smoothly corrects their position or maybe snaps them if the difference is too big.
Right. It makes the experience feel much more immediate and less jerky, even with some network delay.
And on the server side, there's lag compensation.
Yes, this is especially important for combat or aiming. The server might roll back time slightly when processing a player's action, like firing a weapon. It determines what that player saw on their screen when they fired, considering their specific latency.
Applies the shot based on that past world state, and then snaps everyone back to the present, so you can aim directly at the target you see without having to lead them based on your ping.
Exactly. It makes combat feel more responsive for the shooter, though it can occasionally lead to situations where you feel like you were hit by someone already around a corner from your perspective. It's a common trade-off.
And underpinning all this is still the choice between TCP and UDP for reliability.
Still a fundamental choice. TCP gives you guaranteed ordered delivery good for critical things like chat, login, maybe trade confirmations, but it adds overhead and latency. UDP is fast, fire and forget, no guarantees.
So games often use a mix or build their own reliability on top of UDP.
Very common. Use UDP for frequent, time-sensitive updates like player positions, where losing one packet isn't catastrophic and getting an old packet late is worse than getting none. But add custom acknowledgement or retransmission logic for things that must get through but still need low latency. TCP might be reserved for less time-critical, absolutely essential data.
And finally, for these massive worlds, you can't just send every player updates about everything happening everywhere, right?
Absolutely not. That would instantly saturate the network. That's where area of interest management comes in. The server intelligently filters updates.
Only sending you data about things near you.
Essentially. Common methods are grid-based. Dividing the world into squares, you get updates for your square and adjacent ones. Or aura-based, you get updates for everything within a certain radius around your character. This drastically cuts down the amount of network traffic each player needs to send and receive, making large player counts feasible.
Wow. So when you put it all together, the journey from UO's original designs, wrestling with 90s tech, to modern emulators using sophisticated techniques, it's quite a story.
It really is. This deep dive, I think, shows how UO's foundational network communication, its client-server model, its pioneering sharding, its custom protocols, even its struggles with exploits laid so much groundwork.
Yeah, we've traced it from that core architecture through the challenges of reverse engineering, right up to how communities are using modern software like .NET and frameworks like Netty, along with clever patterns like type adapters and RPCs to keep these worlds alive via projects like ServeUO.
And the fascinating thing is the core problems UO faced, cheating, managing latency, ensuring reliability, scaling a persistent world, they're still the fundamental challenges driving innovation in online games, network security, and distributed systems today. The solutions evolve, but the problems endure.
Which leaves us with a thought, maybe. As we keep building these increasingly complex, interconnected digital worlds, what does the future hold for that balance between, say, the server's need for authority, like you are asserted so strongly, and the player's desire for freedom and agency? And how will the hard-won lessons from games like Ultima Online continue to echo and shape the very fabric of our digital lives?